Find the x values, if any, at which f is not continuous and classify them as being removable or non-removable. The first thing I want to talk about here is what does removable mean and what does non-removable mean. So a removable discontinuity is just a hole in the graph. So this would be something like this graph. I'm going to leave it in blue because removable is in blue. And a hole in the graph, that is a removable discontinuity. A non-removable discontinuity would be something like a vertical asymptote that creates a horizontal gap in the graph, or it could be where a function does not meet up. If you think about the definition of continuity when you first learned it as, can you trace this graph with your pencil without lifting it up? Well, if you look at this graph here, this is a discontinuity. So the easiest way to find these is to, in this example anyway, is to find out where any vertical asymptotes are. Those are, or holes in the graph, either one of those. So in order to do that, we need to factor the denominator. So this will be f of x equals x plus 2 over x plus 2 times x minus 5. So there will be two discontinuities here, one at x equals negative 2 and one at x equals positive 5. So I'm going to do this here. X equals negative 2 is a discontinuity, and x equals 5 is a discontinuity. Now, I know already that this x equals negative 2 is removable. And that is because when you look at the function in its factored form, you can reduce the x plus 2 away. And if you remember back to rational functions, when you can cancel a factor, that creates a hole in the graph, much like this blue graph over here. So when you cancel those out, you're left with a 1 in the numerator, so you have a 1 over x minus 5. And if you set this factor equal to 0 and solve for x, you get that x equals 5. There's nothing to cancel with it. That makes this a vertical asymptote, but also that makes this non-removable. So we have two answers here, x equals negative 2 and x equals 5. The negative 2 being non-removable, and the positive 5 being non-removable. In this next example over here, g of x equals tangent of pi over 2x. And there are many ways you could go about this, telling where this graph is not continuous. I think an easy way to do it is to turn this into sine of pi over 2x over cosine of pi over 2x. And what we can do here now is find out where does cosine of pi over 2x equal 0. Because when the cosine equals 0, this entire fraction will be undefined. So the cosine of pi over 2x has a period from, let's say this, from 0 to 4. So the period is 4 units wide. And the cosine graph looks something like this. So in the first fourth it does this, in the second fourth it does this, then it curls back up in the third fourth, and then in the last fourth of the graph, we know it'll be back up at 1. So we are looking for when the cosine is 0, So halfway through the period is this, halfway between 2 and 4 is 3, halfway between 2 and 0 is 1. So it looks like cosine of pi over 2x will equal 0 when x equals 1 and x equals 3. But we could just continue this graph over here like this, and the cosine will also cross at 5 and the cosine will also cross at 7. So there's 6, all right. But it doesn't stop there. We could take this entire graph, copy and paste it on the left-hand side, on the negative side, and we can go in both directions forever and ever and ever. But it looks like this is going to be every single odd number there ever was. So the way to represent odd numbers is to multiply any number by 2 and then add 1 or subtract 1, as long as that number is an integer. And we want to make it a whole number, so as long as k is an integer, that guarantees that we will be substituting a whole number in here. And if you're putting a whole number in here and multiplying it by 2, pick your favorite number, multiply by 2, guaranteed you get something even. But then if you add 1 to your even number, I also guarantee you will get back an odd number. So this expression takes care of any odd number that you'll ever find that this graph is discontinuous at all of those odd numbers. And as a matter of fact, they are non-removable discontinuities. Find the x values, if any, at which f is not continuous and classify them as being removable or non-removable. We just talked about these ideas, what being removable and non-removable means, in the previous page. So we can just dive right in here. We know that in this function, f of x equals x over x squared plus 9, that in order to find any discontinuities, we can take that denominator and set it equal to 0 and solve for x. So we can subtract 9 from both sides and get that. Then we can take the square root of both sides and get x equals plus or minus 3i. Oh, that's weird. We get this imaginary unit here. Imaginary. That's I. We don't have anywhere, we don't deal with these. There's nowhere to graph this if we were looking at a graph. So this means there are no discontinuities for this graph. That's because when we solved set the denominator equal to 0 and solve for x, we got something imaginary. We can't work with those. There are no discontinuities for this function. Cool. All right, well, that was easy enough. Let's look at the next example. The next example, it looks like we have this weird function, this absolute value of x plus 3 over x plus 3. And the easiest way to explain where there is a discontinuity here is to look at what the piecewise function is. So first, I know that any time that you have an absolute value function divided by the function inside of the absolute value, you're either going to get a 1 or a negative 1. The question is, where does this function stop being 1 and start being negative 1, or vice versa? Where does this function stop being negative 1 and start being 1? Well, this all comes from when the absolute value function breaks. And the break I'm talking about is where the absolute value function changes direction. So this absolute value function will look something like this here at -3. This absolute value function changes direction at -3. Now, if you want to think of it, this is just a translation to the left of 3 units. So that's why this graph looks like this. So when you take the positive portion, the positively sloped portion of this, that gives you the equation x plus 3. And when you divide x plus 3 by itself, you get 1. And that happens to the right of 3. So when x is bigger than -3, it happens to the right of -3. When you look at the other branch of the absolute value over here, when we are less than -3, that means we are looking at the opposite of this, so the negative of the negative of x plus 3. So negative x plus 3 over x plus 3 is -1. So here we have this piecewise definition of this absolute value function. From here, you can clearly see that when x is -3 or greater, that we have this function looking like this. So this is at a height of 1. This is -3. So that is the top portion. I'll box it in white. And for the bottom portion, which I will box in blue, says that the graph is -1. I'll put -1 here, all the way to -infinity. It's that height. So there is clearly a discontinuity here. This graph does not meet up at this point. In fact, it's not even defined for an x value of -3. So we can state that there is a non-removable discontinuity at x equals -3. For this example, we're doing something very similar to the previous examples, finding where the removable or non-removable discontinuities are. So in this particular example, we need to check 2 things. The first is, are there any discontinuities of these functions on their respective interval? So we want to know, is the cosine of pi x discontinuous anywhere for x less than 2? And the answer is no. The cosine of this particular argument, pi x, is continuous everywhere. So if we just take a portion of it, say when x is less than 2, it's still continuous. We also need to check that this function, 3x minus 4, is continuous on this interval. So 3x minus 4 is a linear function that is a continuous function. And if we even just take a little bit of it, it's still a continuous function on this interval. So that's the first thing. We just needed to check each individual function for continuity on its respective interval. The second step is to check right here. This function exists for when x is less than 2, and this function exists for when x is greater than or equal to 2. So what we will do is we will take these values 2 and substitute it into each function to make sure that they get the same y value. If we get the same y value, then this whole function is continuous. So let's take a look at cosine of pi times 2. That's what happens when you substitute 2 in for x here. That gives us the cosine of 2 pi, which is 1. The other function is 3x minus 4, but we're substituting 2 in for that x. That gives us 2. So these do not match. So we know that there is a discontinuity at x equals 2. Now, since these two y values do not match, this gives us a non-removable discontinuity because there will be a vertical gap in between these two ordered pairs. So this is a non-removable discontinuity at x equals 2.